A series circuit is formed when electrical components are connected end-to-end in a single continuous chain. One terminal of the battery connects to the first component, the output of that component connects to the next, and this continues until the final component connects back to the other terminal of the battery. This creates only one possible path for current to travel. There are no branches and no alternate routes. Current leaves the positive terminal of the voltage source, flows through each component in turn, and then returns to the negative terminal of the battery. In conventional current flow, we describe current as moving from positive to negative. For circuit analysis and industry practice, we always use conventional current direction. Because there is only one path available, the same current must flow through every component in the circuit. The current cannot split or change between components. It is identical at every point in the loop. Now watch the animation carefully. We will begin with a single lamp connected to the battery. Then a second lamp will be added in series. Then a third lamp will be added. Notice what happens to the brightness of each lamp as more lamps are connected. Do not try to explain it yet, just observe the change. We will analyze the reason shortly. Electric current needs a closed loop. When the path is broken, charges can't circulate. Close the loop by placing the mouse over the switch, and current can flow around the circuit. This figure on the right is the schematic diagram of the battery and light circuit. The power source creates a voltage difference. By convention, current leaves the positive terminal and returns to the negative terminal. A resistor, in this case the light, isn't polarized by itself. Its polarity is defined by current direction. Current enters the plus side and exits the minus side. The resistor absorbs power and dissipates it as heat. This creates a voltage drop between positive and negative. Current in a series circuit is the same through every component. There is only one path for charge to flow, so the total current leaving the source must pass through each element in turn. This means the total current, IT, is equal to I1, I2, and I3 at every point in the circuit. No matter how many components are added in series, the current remains identical through each one because there is no alternative path for it to split. The power supply has a voltage rise, from negative to positive, representing energy being delivered to the circuit. Passive components such as resistors have voltage drops. Using the passive sign convention, the terminal where current enters is marked positive. In a series circuit, the algebraic sum of all voltages around a closed loop is equal to 0. This principle is known as Kirchhoff's voltage law, or KVL. It tells us that energy supplied by the source must be completely accounted for by the voltage drops across the components. When we apply KVL, we assign polarities to each element. As we move around the loop, voltage rises are treated as positive and voltage drops as negative, or vice versa depending on our chosen direction, but we must stay consistent. When all rises and drops are added algebraically, their total equals 0, confirming conservation of energy in the circuit. Kirchhoff's voltage law, or KVL, states that the algebraic sum of all voltages around a closed loop is equal to 0. For a simple series circuit, we can write this as plus Vt minus V1 minus V2 minus V3 equals 0. Rearranging this expression gives us Vt equals V1 plus V2 plus V3. In other words, the source voltage is equal to the sum of all voltage drops across the series components. Now we apply Ohm's law, where voltage equals current multiplied by resistance, V equals IR. Substituting Ohm's law into the equation, we replace each voltage term with I times R. This gives us IRT equals I1R1 plus I2R2 plus I3R3. In a series circuit, the current is the same everywhere. So I equals IT, which equals I1 equals I2 equals I3. Because the current is the same in a series circuit, we can factor it out of the expression. That leaves us with IRT equals I times the quantity R1 plus R2 plus R3. Dividing both sides by I gives us the final result. RT equals R1 plus R2 plus R3. So in a series circuit, total resistance is simply the sum of all individual resistances. If you add another resistor into the series path, you increase the total opposition to current flow.
As a summary, in a series circuit, the current is the same through every component. The total current equals the current through resistor 1, resistor 2, resistor 3, and so on. For voltage, we apply Kirchhoff's voltage law. The total supply voltage is equal to the sum of all individual voltage drops across each component. When calculating resistance in series, we simply add them together. The total resistance equals resistor 1 plus resistor 2 plus resistor 3, and so on. These three relationships, equal current, additive voltage, and additive resistance, fully describe how a series circuit behaves.